Hey there, Calc folks. Back here with what we might think of as another set of lectures and then this series of lectures that I'm putting together for you folks, where we are going to start looking at what we might think of as our first mathematical application of this operation known as a limit, right? To kind of go above and beyond just evaluating limits, be able to look at a little bit of how this is used, and then more specifically, how the limit is used in our mathematical world. All right. Yes, it can be calculated. It can be applied to a function and calculated for an independent variable's behavior. However, we can set that situation up in the mathematical world in several different arrangements, where this limit then can be used to perform some useful mathematical calculations for us. And that's what we start to see in this next set of lectures, right? Let me bring my notes over here, all right? What we are going to be introducing ourselves to is the concept known as the derivative, right? The next set of lectures is going to focus, and the next section of material is going to focus itself on the calculation known as the derivative. And what, again, the derivative is it is our first mathematical application of the use of limits, right? We can use limits to help us calculate a value for a function known as its derivative. And we're going to study this calculation. All right. Now, where this study does begin is with the topic on the board here, right, on my note sheet. And that is the concept or the calculation known as slope of the tangent line, or the problem. This is kind of a classical problem for calculus students, right? Every calculus student looks at this problem and studies it, and it's called the slope of the tangent line problem. All right? It's a problem where we become interested in how do we calculate the slope, the rise over the run calculation, for a line that we know is exactly tangent to another curve, right? We're going to get into that calculation in this video, all right? We're going to study that situation. We're going to set it up and run through a calculation with it. And what this is, this classical problem is, it is our first introduction to the concept of a derivative. What we are actually calculating, and we'll see this defined in our next set of notes, what we're actually calculating when we go through the slope of the tangent line problem is a value that is defined as the derivative calculation. All right? And we're introduced to it here in this classical problem. Now, what we do is we do consider that when a line intersects a curve in mathematics, there are two ways that behavior can occur, we say. Right? When a line intersects a curve, it can either cross through the curve at that point of intersection, or it can just touch the curve at that point of intersection. And I have an illustration here to show you what I mean. Right? When we look at this illustration down here, right? This first illustration, right? The illustration here on the left illustrates this curve in blue and this line being tangent to the curve, right, at this point, right? And what's unique about the line tangent to the curve is that it actually doesn't cross through to the other side of the curve at that point. It maintains its behavior on one side of the curve, right? If we were to orientate ourselves into the XY coordinate space, we would always be above the curve in this orientation, except at the point of tangency where we would be equivalent to the curve. That is a little different than what I see here in the non-tangent situation, right? Where we lack tangent behavior. And at this point of intersection, we actually see the line pass through the curve. It crosses over the curve. It moves from one side of the curve to the other side, right? If we were to put this into an XY coordinate space, it crosses from being greater than the curve to being less than the curve at that point. Right? That is a description of non-tangent behavior. Versus here, what we see is tangent behavior. Right? What we're considering is calculating, how do I calculate the slope of this tangent line to this curve at this particular point? Right? That's going to be our common question. That's not a tough question over here if I happen to know also where this coordinate exists in space, where I know these two coordinates are intersecting our curve. If I was to put these situations into the XY coordinate plane, right? In the XY coordinate plane, in the non-tangent situation, if I know the point of intersection for both of these locations, I can calculate the slope of that non-tangent line by just using the difference between the rise and the run, the rise over the run. I can form that ratio of rise over run, the difference between our x values and our y values for those 2 points, to calculate that slope. But in this tangent situation, if I was to place this in the xy coordinate space, I don't know 2 points on that line. I'm not going to be given 2 points on that line. All I'm going to know is that I'm along this curve and at this point, and I'm interested in what is the slope of that tangent line, right? I will only have this point on the line available to me. I won't have another point to calculate that slope with, right? So that's a bit of a problem. That's where the problem arises here in this classical case of calculating slope of the tangent line. And the way we're going to calculate that slope is with a calculation that involves a limit. And in the process of that limit calculation, we are illustrating the calculation also known in calculus as the derivative calculation. Right? This is our classical slope of the tangent line problem. Now, I do believe we do note that in terms of these behaviors at this point, there will always only be one tangent line at any point along a curve. Whereas there will always be an infinite number of non-tangent lines at a point along the curve. So having some knowledge of this tangency, right, is certainly important to us. This is one of the reasons why we study it. There's only one tangent line. What is it at this point, right? We can define any infinite number of lines that are not tangent, but how do we go about defining the one tangent line, right? That's a question we're concerned with. And all we need is the slope and the point of tangency. The slope becomes the unknown factor, right? Now, to begin with, if we consider being in the xy coordinate space, right, the line tangent to the curve is going to be described by the equation y equals mx plus b, right? We can see here I've placed this situation into my xy coordinate space. And the line of tangency here to this curve, right, is going to be described by the line y equals mx plus b, right? Again, where m is going to be the slope of that line, and 0 comma b is going to be where it would intersect the y-axis. It would be the y-intercept, right? So we might be interested in, well, what's the equation of this tangent line at a particular location on this curve y equals f of x? Right? Well, to identify the slope of this tangent line, what we have to identify is the value of m in this equation. And the way we do that is with the use of a limit. All right? A limit applied to a functional behavior describing the slope of the secant line passing through that point of tangency. What's a secant line? Well, a secant line is a line that intersects the curve at two locations, passing through the curve at each. Right? And I guess it doesn't have to pass through. You could have a secant line that's tangent at one, but crosses through at the other. So it has to cross through at least the curve at one of those points of intersection. Right? And what we can do is examine the slope of that secant line where the distance between the 2 points defining the secant line on that curve move towards each other, or the distance between them approaches the value of 0. And if we hold one of those points constant at that point of tangency, and we move the other one towards it, what we will see is the secant line slope it'll behave in a manner that will become the slope of the tangent line in a limit behavior. Right? If we consider the following illustration, this is how we're going to set ourselves up. We're going to consider what is the slope of the secant line passing through the curve at these 2 points. We're going to define one of the points at tangency being at x equal to a, and it's going to have its output at f of a. And then we're going to place the other point on the curve at a certain horizontal distance away from a. That's what h stands for. It's this horizontal distance that we are away from a on the curve. So its location is going to be at a plus h, and it's going to have its output at f at a plus h. And what this gives me is my rise and my run. My rise for this slope is the difference between f at a plus h and f of a, and my run is the difference between a and a plus h, which simplifies to the statement of just the value of h. Right? So it's f of a plus h minus f of a divided by h. That would be the slope of that secant line. Right? And we would take note of that here. Again, the slope of the secant line passing through the point a comma f of a right here, and the location a plus h f at a plus h right here would be just given by our slope formula, rise over run. Here's our rise in the numerator, here's our run in the denominator. And what I do with this functional behavior, right, being a function of the variable h is what we're going to see. We're going to allow that h to vary by allowing it to get smaller and smaller and smaller and approach the value of 0. We're going to bring in this location here at a plus h closer and closer and closer to the value of a. And we're going to do that using a limit. And when we do that using a limit, applying a limit, we will end up with what we call slope of the tangent line. Now, I do follow with a formal definition here, and you can read through that. For slope of the secant line along a function. But here is what I want to illustrate. This is where we're going to get the slope of the tangent line. As for the slope of the tangent line, we're going to take that slope of the secant line calculation that we have above right here, and we're going to allow that value of h, that horizontal distance between our two locations of secant behavior, and make that value approach 0. We're going to bring in that second point closer and closer and closer to the first. And what we're going to see is that the slope of the secant line is going to become the slope of the tangent in a limits evaluation. we're going to have the limit as h heads to 0 for this ratio. F at a plus h minus f of a all divided by h. That will yield the slope of the tangent line, right? Tangent to the curve f at the value of x equal to a. Okay. If we were to illustrate this, I do give you a static illustration here in the notes. Right? What the static illustration is showing you is moving this h value, or making this h value shorter and shorter, will move in this second coordinate closer and closer to the first where we would expect our tangent behavior. The tangent line being illustrated in red. And you can see as that h value gets smaller and smaller and smaller, the slope of the black line in this graph is going to get closer and closer to the slope of the tangent, the red line in this graph. The slope of the secant line, the black line in this graph, is going to get closer and closer and closer. From here, it gets closer here, and it even gets closer here as we make this value of h smaller and smaller, as we have it approach the value of 0. Right? What we're illustrating as h approaches 0, the slope of the secant is going to get closer and closer to the slope of the tangent. Another way I have to illustrate this for you, folks, let me bring this up. This is a little just a demo to illustrate this that's a little bit more dynamic. This is a very similar illustration here. I did add a few more labels in. But this is a bit more dynamic of an illustration to kind of show you what's going on in that calculation. We are looking at the function given by the ratio of this difference with this difference here. The ratio of f of a plus h over f of a divided by this statement, this value of h. And what we're going to see is if I make this h smaller and smaller and smaller, which I am able to do with the slider bar here at the top of this demo, we will see that the secant line passing through these two locations at a and a plus h is actually going to move in towards what is the graph of the tangent line at this point, a comma f at a plus h. And you can see as I move in the slider, that secant line, the green line, is becoming more and more similar to its slope of the tangent line, right? They're almost becoming one and the same line here as I get closer and closer. And you can see we're almost there. Oh, just about. Right there, that h value is 0. And we no longer see the secant line because the secant line is transformed into the tangent. Right? Well, what we can study, right? What we can study in this setup is the function that forms between the difference of f of a plus h and f of a over the value of h, where h is the variable, right? It's what's varying here in this illustration. And as the illustration illustrates, it's approaching 0. And as it approaches 0, we would expect the slope of the green line to get closer and closer and closer to the slope of the red line. At the point where, when we actually have 0 distance between those 2 points, the slope of the secant would be equivalent to the slope of the tangent. Or really what would happen is the slope of the secant would no longer exist. The secant line would disappear. Right? It would no longer exist, and we would have just the tangent line. And we can calculate that slope's behavior for the tangent, not needing 2 points on that line, by just exploring that behavior of the change, right, in rise over run as h changes. Right? That is how we're answering this problem. All right? Let me go back to my notes here. this back up. So that is what we're trying to illustrate here in this static illustration. All right, now let me scroll down. So I'm going to take a quick break here. All right, let's see here. Where we go from here, I believe, is into an example. Right. We might consider the curve. Here I have 6 minus the quantity x minus 3 squared. All right, let's consider this curve right here. The slope of the secant line passing through the point of tangency at a value of x equal to 1, perhaps, is going to be described by this calculation here. As we had said, it's going to be f at 1 plus h, because 1 is our point of tangency, minus f at 1, again, because 1 is our point of tangency, all divided by h. H, again, being that horizontal distance between our point of tangency, we can see in these illustrations right above, and that second point on the secant line. And what we're going to do is that's going to become a function of h now. And this function of h can be evaluated as a limit where h heads off to the value of infinity. Now, I do believe we set it up first with the slope of the secant function. Right? Yep, we do. We calculate f of 1, substitute 1 into that function. You will see you get the value of 2. All right, we worked through the algebra there. 1 minus 3 is negative 2. Squared is 4. 4 minus 4 subtracted from 6. We can see results in 2. All right. And if we calculate that value at 1 plus h, all we are doing is substituting into that quadratic. My apologies. That quantity 1 plus h. Everywhere we see an x, so it goes into right here where we see this x. We substitute in 1 plus h. So it's going to be 1 plus h minus 3 inside that group. And that's what we see to begin with here. 1 plus h minus 3 inside that group. Now we know 1 minus 3 is negative 2, so I could write that as h minus 2 inside that group. If I square that, that will square out to become the quadratic h squared minus 4h plus 4. If I distribute the negative and add the 6, I will end up with 2 plus 4h minus h squared as the value for f at 1 plus h. Now, if I take 1 plus f at 1 plus h and I take away f at 1, notice how that simplifies. If I take f at 1 plus h and I take away f at 1, it does simplify into 4h minus h squared, all divided by the quantity h when we calculate the slope of our secant line. All right? And you'll notice that in this quantity 4h minus h squared, you do have a common factor of h, where when factored out can be canceled with the h in the denominator, leaving you with just 4 minus h in the numerator over the value of 1. So all this just simplifies to the statement 4 minus h. All right? Some pretty basic algebra. Now what that does is describes what we call the slope of the secant line function in this case. The slope of the secant line where that second point could be at any distance h from the first. All right? If it's 1 unit away, you'd have a slope of 3. If it's 5 units away, you'd have a slope of negative 1. Because 4 minus 5 is negative 1. If it's 0 units away, you have a slope of what? You can see it's going to be a slope of 4. In fact, that is how we think about the slope of the tangent line. The slope of the secant line function is described by 4 minus h. at a location of tangent c that is x equal to 1. So by definition, the slope of the line tangent to y equal to f of x then is going to be the limit as h heads to 0 for that slope of the secant line, which is going to be the limit as h heads to 0 for 4 minus the quantity of h. And what's the limit as h heads to 0 for 4 minus h? Well, from just substituting in 0 for that value of h, you have 4 minus 0, and that results in the value of 4. The slope of the line tangent to this curve at the value of 1, that being our location of tangent c, is equal to the value of 4. And we calculated that with the slope of a limit applied to the slope of the secant line. Now, do we actually find the line itself? I think so. As for the actual equation of the tangent line, right? Notice we could plug that 4 into our equation now, y equals mx plus b for the value of m. And that would give me y equals 4 times x plus b. And to find b, one of the quickest ways to do that is just to take one of your coordinates, substitute it in for x and y into the statement where you know m is also the value of 4, and to solve that statement for the value of b. All right. Here I have the equation y equals mx plus b, where I made y the value of 2, m4, and x1 using this coordinate 1, 2, and this slope of 4. Simplifying that, I will find b is equal to negative 2. Right? 2 minus 4. Take away the 4 from the right side to move it to the left, and you end up with b equals negative 2 in value. So in the end here, I do think this is the end. Oh, besides other than a graph. The equation of the tangent line, right? The line tangent to the function 6 minus the quantity x minus 3 squared at x equal to 1 must be described by y equals mx plus b, where m is 4 and b is negative 2. This equation y equals 4x minus 2. Where I do graph both those equations and show you that they are indeed tangent. Notice this is the graph of those two equations. Right? This is the graph of that parabolic curve, 6 minus the quantity of x minus 3 squared. We can see it is a parabola, a quadratic equation with a vertex at 3, 6. And a vertical stretch of negative 1. That gives me this blue graph here in space. The tangent line is described by the equation 4x minus 2 with the slope of 4. That means it rises 4 and runs 1 to move between these 2 points. And it has a y-intercept down here at negative 2. And all of that is true in this graph. We can see it all fits this illustration. This is called the slope of the tangent line problem, folks. And you can see here it's a math problem. It's like, how do we find the equation of this line tangent to this curve at this point? If all I know to begin with is how to define the curve and where I want to find the tangent line. Well, I can apply limits to the description of the slope of the secant line. And I can apply it in general as we've defined up here. Right? It's defined in general as this, where you can set up the slope of the secant line as f of a plus h minus f of a divided by h. And this is how we go about answering that classical problem from calculus. Right? It is this application of limits, right, applied to what we already understand is a slope formulation, a rise over a run calculation, where we explore the rise over runs formulation, its behavior, as the distance between the 2 points decreases, where this h value becomes smaller and smaller and smaller. Right? This is also related to what we opened with, and that's the idea that this is all just a derivative calculation, folks. What we're going to find, if we go all the way back to the top here, this is all just a study of derivatives. As we're going to see in the next next video, the next little section of notes here that follows this topic, is that this definition that we developed, not the formula one, but this is slope formula up here, but the second one for slope of the tangent line, that is actually formally known as the derivative of a function at the value of x equal to a. This is officially known as the derivative of f, right? The function f at the value of x equal to a. We've just taken that generic understanding of derivative and have shown that what it does give us as a bit of information can be interpreted as slope of the line tangent to our curve. All right? All for the next video, folks. So with that said, I do think I'm going to end there. And I will try to post up a video here soon for the next topic, getting into this formal definition, folks. So hope you're all doing well, and I will see you next time.